Hi there, let's deal with rockets, satellites, space probes, and how GPS works. So how did we figure out how rockets work? Well, believe it or not, uh, at that time it was a Nazi, uh, and so Karl von Braun was the first to come up with the idea of rockets in World War II, and there he is behind Hitler right there, Karl von Braun. Rockets come in different sizes, and we call them stages. And so staged rockets often, what will happen is it'll lose part of its first section, and that will make it lighter. So for example, if you look at this one, it's got thrusters there, and then this section falls off. It's got thrusters there, and so on. So different stages, once they use up their fuel, it's dropped off, and so it's lighter. Usually the payload is at the top of the rocket, so the astronauts and anything they're carrying, and this part is dropped off. How does rockets work forward, or how do they work? Well, Newton's laws of physics say for every action, there's an equal and opposite reaction. So like a balloon, the air moves this way, and the balloon moves in the opposite direction. Well, that fundamental law of physics is what we get for thrust for a rocket. So here it is again, action, reaction. So let's keep going on this then. How do rockets, once they're in deeper space, be able to move forward? Well, the issue becomes, what are we using for fuel? Once you're in space, there's no more oxygen, and we can't use combustion to act as thrusters where we ignite fuel in a combustion reaction. So sometimes we use gravity with rockets and certain probes or satellites. And so what will happen is the Earth sends a object like a rocket ship, and we can slingshot it thanks to the gravitational pull of an planet. So for example, Jupiter is how we sent some of our deeper space probes further outside of our solar system. So the planet's gravity can help slingshot. We've also come up with, which is how one of our deep space probes is operating, we've come up with ways for propulsion that don't require combustion, and they're called ion drives. And so what happens is we can use ionic fields to help generate a tiny ion beam of propulsion. It's not very strong, but strong enough because if you remember, in space there isn't a lot of gravity. Let's talk about the Earth's satellites. There are two types of satellites that we set out on Earth with, and one is called a geosynchronous satellite. And what that means is it's at just the right distance away from the Earth such that it rotates exactly at the same speed as the Earth is rotating on its axis. So that's a geosynchronous satellite. The other kind that we have is called low Earth orbit, and the low Earth orbit will spin much faster than the spin of Earth. The closer you are to Earth, the stronger the pull, and so the more thrust you can get to go around and around. How do satellites stay in orbit? Well, a combination of forward propulsion along with the Earth's gravitational pull. How do we get out of the Earth's gravitational pull? Well, the concept is called escape velocity. Escape velocity is the speed at which the centripetal force outward exceeds the pull inward. And so each planet has a different pull of gravity. So if the object's moving faster than the escape velocity, it'll be able to launch itself from Earth and head towards the solar system or the moon. So Earth's approximate escape velocity is 8 kilometers per second. So if it travels faster than that, away it goes outside of the pull of gravity. Look at how escape velocities compare with other planets. The moon, 2.8. Look at Venus, 12. And of course, Jupiter, which is the biggest planet and therefore the strongest gravitational pull, is 69. We can talk about our space shuttle. Our space shuttle has many purposes. One of them is to take stuff up to the International Space Station. So it acts as basically a vehicle to transport things back and forth. We also put satellites into here, so some companies will pay NASA to put satellites into here, and then it launches a satellite into orbit. The International Space Station, or the Space Shuttle, can also do scientific experiments, so it has lots of purposes. We don't have any more new space shuttles. All the space shuttles are going to be retired at the end of this year, and so there's been several. Some have been disastrous, like on February 1st, Space Shuttle Columbia. Let's talk about the International Space Station. The different colors represent which countries have helped do what. So the red is Russia. Look at all the yellow. That represents the pieces that the United States have done. Japan in pink, Canada in blue, and one of the things you'll notice here is the Canadarm. So it's a very famous arm that they use. Italy and Brazil is in the purple. So very much an international endeavor, and they do experiments up here, and it's a great place. Here's our Canadarm, and so it helps do a bunch of things so that astronauts don't always have to go on a spacewalk. Spacewalks are really dangerous because if something happens and their suit gets ripped or if they lose their tether, then they float away, and so it's easier to stay inside the space station and do a bunch of work with the robotic arm called the Canadarm. You can actually see the space station going around the Earth's orbit. Let's look at the video clip on space satellites.
What are you up to? Making a satellite? Okay. Dear Tim and Moby, what are satellites? From Elena. Technically, a satellite is any object that orbits around another object. The moon is Earth's natural satellite, and the Earth and other planets are satellites of the sun. But the type of satellite you're probably thinking of is an artificial satellite. Satellites receive and transmit valuable information, everything from communications, weather images, navigational data, and even images from deep space. Satellites let us see news from other parts of the world as it's happening. Using radio waves, images and sound can be transmitted quickly from one part of the Earth to another. Information from one side of the world can be beamed up to a satellite, which instantly transmits it to the opposite side. Satellites come in all sorts of shapes and sizes, but they often have some common parts. An onboard computer monitors the different systems. Solar panel cells trap sunlight and convert it into electricity to power the satellite. Batteries store power. Radio equipment, like an antenna and receiver dish, let the satellite communicate with Earth and other satellites. An attitude control system keeps the satellite pointed in the right direction. Well, usually satellites are put into orbit by rockets. When the rocket reaches extremely thin air, at almost 200 kilometers up, it fires off small rockets to get into a horizontal position. Then it releases the satellite into orbit. Well, the path that a satellite follows depends on the job it has to do. For satellites around the Earth, their orbit is often based on a particular distance from the ground or what direction it's orbiting. For instance, a low Earth orbit is easy to reach, and it's good for space station and space shuttle missions. Low Earth orbits are those under 2,000 kilometers from Earth's surface. A satellite in geosynchronous orbit is always over the same spot, which is good if it's a communications satellite. Geosynchronous translates roughly to same time as the Earth. These satellites orbit the Earth at the same rate as the planet's rotation. How do you plan on getting that into orbit?